And this is bringing up the idea of non-parallel synthesis. And maybe it's easier to first demonstrate this just using generic letters. Now, in terms of a synthesis, one way to think about it is we could have a parallel synthesis. This is what we've been doing for the most part. A goes to B, B goes to C, and so on. And you just turn one compound into another. That's not necessarily how it has to be done. So we could end up having something where you make a reagent. Here A turns into B. Here you turn reagent X into reagent Y, and then you combine these two reagents together in a particular step to make, B, Y, or something like that. That's going to come together to be a new compound. So a lot of times what you're going to be doing is you would make a variety of different compounds. Let's just say they're in different vials. And then you might take something from one vial that you've made and add it to something else in another vial. So let's use an example hopefully to help clarify. Let's say we need to make this. This is a way you oftentimes see these synthesis problems. We want to make this particular ketone, and there's a limitation on it. We need to start from alcohols 6 carbons or less. So that's a limitation. So this is what we want. This is the final product. But we can only use alcohols as our starting materials, and they all have to contain 6 carbons or less. We can use any other reagent that we want. So any sort of magnesium or other acids and bases. However, all of the carbons that are in this final product have to come from alcohols that are 6 carbons or less. And this is kind of intentionally done because you notice that there's more than 6 carbons here. So what we can think about doing is, let's do this retrosynthetically first. Is we have this 6-membered ring. Just redraw this here. And we probably want to think about where can we break this apart conceptually. Well, we have this ketone as a functional group, so we could probably break it either on this bond here, which would give us, that would be 6 carbons, and then something that's 3 carbons. Or conceptually, we could break this carbon-carbon bond through a Grignard reaction in the forward direction. But then we have more than 6 carbons. So why don't we just go ahead and mentally, we're going to disconnect or break that bond. So now in retrosynthesis, that's going to give us something that we would be able to break that bond. However, we first need to think about, let's just go ahead and do it then. We probably want to make that from an alcohol, and then we could break that bond into, say, something that is a Grignard reagent, and how about this aldehyde as our product? So we could actually, in the forward direction here, take this Grignard reagent, have it attack here. That's going to give us this product. It's here, which then we would oxidize to give us our final product. So that's actually the key carbon-carbon formation step, bond formation step here. But then the problem is that these two species are not alcohols, 6 carbons or less. So then what we would do is, I'll just try to kind of keep them apart here. We could make this Grignard reagent from this alkyl bromide. We know ways of replacing or introducing a bromide from an alcohol. So we could do that. And so that's all good. Now we have our alcohol 6 carbons or less. And then all we have to do with our aldehyde is, we know that aldehyde, it's not drawn well, is this aldehyde could be made from an alcohol. I'll just draw in the same format, 6 carbons or less. So that's propanol. I can draw that better, I think. Okay. So now we have our two starting materials, cyclohexanol, alcohol 6 carbons or less, and propanol, 6 carbons or less. So then in order to actually go forward, we would know that we would oxidize this. I won't write it all out if that's okay. We would oxidize this with PCC to make this. We could do an elimination in a HBr addition if we wanted to generate this, or turn this into a good leaving group and displace it with bromide. To make this, turn this into the Grignard reagent. Now bring these two species together to give us this one here, and then oxidize this with either the chromic acid or PCC to give us the final product. So it's a lot of different ways of thinking about reaction synthesis, bringing all this together, and thinking forwards and backwards is the challenging part. What makes it easier is finding the patterns and seeing things like where, right now, I want to form a carbon-carbon bond, or backwards, I want to break the bond, then thinking about where that's going to happen, and then designing your synthesis around a Grignard reaction, for example. And that's when we'll see that forming carbon-carbon bonds is one of the key things in synthesis. So for this summer, we're not going to focus too much on this. I'm not going to ask us to have 10-step synthetic problems, but just to be aware of it. And we'll sprinkle it in a little bit here and there as we see some new reactions. But I want us to be aware of the importance of synthetic chemistry, of taking smaller compounds and making them larger, and thinking about the systematic approach that's used in this. And this is only the tip of the iceberg. If you're really interested in synthetic chemistry, I encourage you to look more into this. Okay, so now how about any questions or comments about this brief run through of synthesis?